speed of light squared. Now, the speed of light is 3 times 10 to the 8 meters per second. It's a very big number. But if you have enough energy, E, you can make new particles of mass m, as long as you have enough energy by a factor of c squared to do it. So if we use that to look at these diagrams, you can see that there's a bit of a problem, in fact, because we would have collided these guys at very high energy. So E is very large. Energy is conserved. So the energy of this photon has to be the same as the energy of the summed energy of these two. And the energy of these two at the end has to be the same as the energy put in. This energy is conserved. But there's a problem there because photons have no mass. So where's the energy gone in the middle here? You've got E equals mc squared. E has to be the same all the way, and it's large, it's not 0. But mc squared, if m is 0, sounds like it should be 0. And the answer to that is in the fact that these cartoons are actually representations of quantum mechanics, and this is the key concept of the talk, in terms of the physics. That we represent interactions by the exchange of virtual particles. And what virtual means is that it doesn't have to have the right mass. So it's one of those examples that in quantum mechanics you can cheat sometimes. Everything what's the phrase, everything that can happen will happen. Well, everything that can happen will happen at some level. There's some probability attached to that. And what happens in these kind of diagrams is all we can actually observe is what went in and what comes out. So everything in the middle is at some level a mathematical idea, a mathematical construct. But if you put the right ideas in, you get the right answer to a very high level of precision at the end. So there's some meaning to that. And the thing that you have to put in, which was the key concept of Feynman's QED, and also of the other theories that we use here, is this probability of the exchange in the middle is proportional to 1 minus q squared minus m squared. Now, in that, the q squared and the m squared, the q is the mass the photon has to have in order to make sure energy balances throughout the diagram. The m is the mass it really ought to have if it was a real photon, which is actually 0, because photons should have no mass. So you can see that this would just be 1 over q squared here, if in the case of the photon, and it means that the further away the photon has to be from its correct mass, the less likely this thing is to happen. So I said all that in words, but you can now understand one of the most important diagrams in physics, and I'll show you why in a second. When we collided this, first we collided it at 91 GeV inlet, and there was a reason for that, because there's a particle called the Z boson, which has a mass of 91 GeV over c squared. So if you do the sums, actually that can have exactly the mass it means to have in that diagram. So the 1 over q squared minus m squared would be 1 over 0, which is a very big number. Now it's not infinity because there are other terms that come in, but it's still a very big number. And this allows you to understand, sorry about the effects there, what's going on. But this is one of the most important diagrams in physics, and not only is it important, one of the most important data sets in physics, and not only is it important, if you can understand this, then you will have no trouble understanding the discovery of the Higgs boson. So what you see here is, as a function of the energy of the electron and the positron that are annihilating, this is the energy here, central mass energy, the probability of the thing happening. So cross-section is just the number of times it happens, or the probability of it happening. And you can see the photon wants to have no mass. So and as you take the photon away and away and away from mass of 0, this probability drops like crazy. It's 1 over q squared. It's just going like that, 1 over q squared minus 0 squared that I had in the equation. But then as you get towards the Z boson, which wants to have a mass of 91 GeV, then you get an enhancement. It's a resonance, basically. You get a 1 over 0 kind of term comes in that's moderated by other things that you don't need to worry about, but stops it going to infinity. But there's a real peak there. And that's because the Z boson in the middle of this diagram can have the right mass. So the quantum mechanical probability of that thing happening becomes much enhanced, and that's a resonant phenomenon. That's what it means to discover a new particle. Because you've got a term in there where there's a new mass, which is the mass of the new particle, and it gives you this enhancement, this resonant enhancement. And we can do the same thing at the Large Hadron Collider. This bump here is the same thing. It's a Z, and this time it's a quark and an antiquark annihilating to give you a Z in the middle. And you can see that we can reach to much higher energies. That's why we built the Large Hadron Collider. We can go up to much, much higher energies than we had here. Here you see it stopping at about 120, or in the data it even stops before that. But here, it's going right up to 1,000, 2,000 even. And these bumps here, the little colourful ones, they're kind of the imaginings of theorists. What if there was a new particle there with a bump? And we're always looking at those to see if there is anything there. So far, nothing. You'd have heard about it if there was, not in this process. But of course, we'll get on to how we see evidence for the Higgs boson in a moment. Okay, so that's the key thing here, is this exchange of virtual particles. And if there's a new virtual particle with a given mass, you'll get a bump in your distribution at that mass. Okay, so back to this now. And as I said, the key thing here in this list of particles is the relationship between the photon and the W and the Z. And I want to show you another diagram, which is actually from my experiment as a PhD student in Hamburg. And this is another key data set in physics that you can understand with just the same principles that I showed you before. There's nothing new here. So what we were doing here was colliding electrons and protons with each other, so bouncing an electron off a proton. Most of the time when you bounce an electron off a proton, it swaps a photon, which has 0 mass. And that's the blue stuff here. The line is the theory and the points are the data. So the electron comes in, smashes up the proton, but we don't really care about that. And the electron bounces off and we measure where it went. That's an electromagnetic interaction. It's a photon exchange. The red line on there and the points is when something else happens, is when it's a weak interaction and you swap a W boson. W boson carries some charge. So when an electron swaps a W boson in bouncing off of a proton, the electron actually turns into a neutrino. And actually, we don't see that. It goes away. But we can measure the process. We can see how often it happens. And you can see here, this is just the energy or the mass of the thing. And this is the probability of it happening. And you can see, again, that's why we call it the weak force. This is a logarithmic scale. It's many orders of magnitude in everyday life at relatively low energies. Many more orders of magnitude more likely to be an electromagnetic exchange, to exchange a photon, than it is to exchange a W, which is a weak exchange. But as you go up in energy, a slightly weird thing happens. Both of them are getting weaker, less likely, because higher energy is more difficult. But they're converging. They're coming together. And you can see around here, they converge. And there's a unification of the two forces there. What that's saying is that the energies, this is in the collisions we were doing in Hamburg back then, that at those energies, the weak force is actually wrongly named. It's no weaker than the electromagnetic force. In fact, it's the same strength. Those two forces have unified. And you can see that written on here, the unification here. Now, there are other unifications on here. There's, maybe the strong force unifies, maybe even gravity unifies, very ambitious. We don't know. That's speculation. There's evidence for some of it, but it's not experimentally known. But this is different. This is data. These points here are actually measured. They're not, the theory agrees with them, the theory is the lines, but the points are the data, and they're measured. This really happens. And, as you go back up and up in energy, in the end you get towards the energy of the Big Bang. But so let's be more workaday and just say, hey, we know two forces of nature here that unify. Why does that happen? Can we understand it? Well, you already know the answer. The answer is, that, in fact, the one key thing I haven't told you that you didn't know is that the W and the Z are heavy, and the photon has 0 mass. W and the Z have a lot of mass. That already tells you why it's a lot easier to swap photons at low energy, because they're nearly at the right mass. They're 0 mass. It's easy to swap a 0 mass thing. As you go up in energy, the photon has to be further and further away from 0 mass in order to conserve energy. The W and the Z are far away from that already here because they need a lot of mass, and it's very hard to create that mass. The energy needed to swap a W or a Z is a long way, is at very high energies. It's a long way away at this low energies. And that's the entire reason the weak force is weak. It's because it's difficult to swap a heavy object. The W and the Z are heavy. As you go up in energy, that fact becomes less and less important because there's so much energy around, you can make W's and Z's like nobody's business, just as easy as making a photon. And that's this unification. So this unification, and in fact the splitting, the fact that the W and the Z weak force and the electromagnetic force look very different at low energies, is due to the mass. It's due to the mass of the W and the Z. And that's where the Higgs comes in. So I'm not going to go through that slide because I can come back to it if there are questions. But, well, let me see. Yeah, I will do that. Sorry. This is solid state physics. So what we have in this initial diagram here, just to go back one, what we have here is a symmetry between the forces, which is broken in everyday life. Okay? So they're the same here. You can swap the weak and electromagnetic force for each other, and it makes very little difference to the whole physical system. But in everyday life, they're hugely different things. The weak force you hardly ever come across. It's beta decay. It's not much going on there. Whereas the electromagnetic force is ubiquitous. It's electricity and magnetism. So this symmetry that's there at high energies is completely broken at low energies. It's just not there in nature. Now, there was a Nobel Prize awarded in 1999 for Tufte and Veltman working out from the maths, that if you say that you absolutely need these symmetries to make the whole of the standard model of particle physics, the whole of quantum field theory doesn't work if these symmetries are broken. Now, that's a really big problem because obviously these symmetries are broken in everyday life. And in fact, what they proved was that massive particles break the symmetry. So you can't have a theory that works, on the one hand, with a broken symmetry. But as soon as you give any of the particles mass, you break the symmetry. And you can see there's a problem there because we know that particles have mass. So it just tells you you've got a great theory, but it's completely useless because it only describes massless particles. So the big excitement about the Higgs boson is that it allows us to bridge that gap. So what you do is you say, I'm going to introduce a field that fills the whole universe, quite a radical step. And I'm going to say that that field will break the symmetry at low energies, but the symmetry is still there at high energies. Now, I know that doesn't mean a huge amount at the moment, but it's a concept called hidden symmetry or spontaneous symmetry breaking. And the best example, which is the plot that I had here, actually comes from actual magnetism, from condensed matter physics, which is where some of these ideas came from in the first place. Electromagnetism is completely symmetric. It has no particular direction. It's spherically symmetric. So you can choose whichever axis to be your x-axis in a diagram you want. And that's the situation here. These are magnetic dipoles jiggling around at high energies. As you cool them down, they like to line up because that's a lower energy configuration. They could line up in any direction, but they like to be lining in the same direction. So there's a thing called the Curie temperature. If you heat some magnetic material, and as you cool it down, what had no net north and south poles, suddenly a north and south pole appear, and you've broken a symmetry. There was a spherical symmetry to the whole system, and suddenly you've picked a direction. You've got a north pole and a south pole. Do it a million times, the north pole and the south pole will be a different way every time, so the symmetry is sort of still there. But for a particular magnet, you've broken it completely. You've picked a north and a south pole. That's what the Higgs does for us. It says that at very high energies, the theory has all these symmetries there. Everything's massless, effectively. As you cool them down, they pick up mass, it breaks the symmetry. And that's exactly what's happening. So this is what would happen here in this diagram. Two of these guys would line up, and that would encourage a third to line up with them, and a fourth. If they're heated up again, there's so much energy, they disalign themselves again. But if you cool them down, in the end, they'll all line up in the same way. And that's the same physical process as to what's going on here, where the two forces are completely symmetric, but as you cool them down, the W and the Z go off in one direction, pick up mass. The photon doesn't and stays massless, and you end up breaking the symmetry between these two forces. So it's an analogy, but it's a proper mathematical physics analogy as to what's going on. And it's the Higgs field, it's the interactions with the Higgs field that actually do that. Okay, so in the last couple of minutes, just to show you the data then, what we do is we measure photons and muons. I said, for instance, in the detector, this is an example of a collision with two photons. These are photons leaving energy in the calorimeter here. No track pointing to it because the photon doesn't have any charge. And this is another plot, like the other two plots that I showed you, and this is one of the plots that caused all the fuss on July the 4th this year. So what you have along the bottom here is the mass. Don't worry about this bottom half of the plot here, but just look at this bit. You have the mass along here, the mass of the photon pair. Here you have